All right. Well, yes, I must apologize once again for this change, but one of my schools changed my schedule. One of my other schools changed my schedule without my knowing about it. So unfortunately for this week, we'll have to start early. Anyway, so a few things I want to go over with you today. Let's go to Moodle for a second. Let's see, I thought I had it open. Here it is. Okay. So I posted basically everything else we'll need. We have the chapter 10. Okay, now remember chapter 10 is the end of the course. We're about halfway through 9, and we also have 10. There's a problem set for 10. Oh, wait a minute. Now, did I put up chapter 9 problem set? Yes, I did. Okay, there's 9, there's 10. 8 you should have already done over the weekend. So, and then now, even though I'm still working on this corrections, the solutions are here for the chapters 3, 5, 6, and 7 problem sets if you want to look at them while you're working on your midterm. I'm aiming to have the rest of the corrections done by tonight or first thing tomorrow morning. So, but in the meantime, you can look at the answers here. So the midterm is due on Wednesday. Wednesday, when I say Wednesday, I mean like Wednesday at midnight. Okay. So you've basically got roughly three more days to finish the midterm. So if you need to review with these problem sets, it's all right here. Okay, so that way you've got that going. Now, here's one thing I do want to mention. I thought, we've only got the 3 more classes left, and chapters 9 and 10 are pretty advanced material, and I don't want to rush through them too quickly. So what I thought we could do here, because normally we would just go through 9 and 10, we'd go through the problems, we'd have a sample final and all of this and that. So if you recall from the syllabus, we're scheduled to have problem sets, which of course we've been doing and a midterm. So now there's a final listed here, 35%, which was intended to be on chapters 8, 9, and 10. So because I don't think we will have time to properly review for the final, what I thought we could do is replace the final exam with the problem sets for chapters 8, 9, and 10. All right, so in other words, what will happen is, and they're already on Moodle, instead of handing me a final exam, you can just submit 8, 9, and 10. I will average them out, and that will be your final exam score. And that will take up 35% of your grade. The midterm is 30. And then these first 4, 3, 6, 5, 6, and 7, the average there would be your problem set average. All right, does that sound like a good idea? I bet you do. So I've just saved you from having to take an actual final exam. But remember, instead, we'll just do these 3. That will be your, quote, final exam, okay? And that way we should have time. So this way we don't have to spend time reviewing for the final. Instead, we'll just finish the chapters. We'll go through them. And then when the course is done on Wednesday, I don't remember what day I said you could hand them in. That was in one of my announcements. Usually a class like this, we'd have a minimum of 3 days after it's over to hand in the grades. So let me go back to Moodle now. And let me just quickly remind myself. Final, yes. Monday the 5th. Oh, okay. Well, because next Monday is the 5th, isn't it? It's hard to believe, is that right? No, that can't be right. I guess it is. Man, how time flies. So I'm going to make a new announcement here right now so we don't forget. So due to time constraints, the final exam will be replaced by the chapter 8, 9, and 10 problem sets. Okay, so that's how we'll have calculate your final exam score. So in other words, I'll average these 3 outs, these 3 together. That will be your final exam score, and they will be due. Chapter 8 has already been done, but since you have already completed the chapter 8 problem set, presumably or you're still just about to hand it in to me, this means that you will only have to submit the chapter 9 and 10 problem sets on July 5th. Okay, so I've basically, this should save you some time because you're just doing those last 2 problem sets instead of a full-blown final exam. Okay, so I think that'll work out. It's the same material anyway, so you'll be covering the same content. You just won't have quite as much time. You won't have to spend so much time on it. So this way, we won't have to rush through the remaining chapter and a half because they're awfully important and they're very complicated as well. In fact, if you do go on and take another course in statistics, the content of chapter 10 is where you'll probably start, and that would be the like sort of like the bridge between this class and whatever comes next. All right, so so here's what we're going to do right now. We're going to go back to chapter 9 and go through that, and along the way I'll also of course show you calculator tricks to get this done a little quicker. So let's just quickly review what we've been doing just for a couple of minutes. We're doing confidence intervals in this chapter, which is a range of values, which is assumed to contain the parameter of interest, for example, the population mean. So here, for example, is a simple case. We've determined through our research that 95%, or with 95% confidence, the mean gas price in the United States is between $2.99 a gallon and $3.39 a gallon. And the reason why it's a range is because it shows that there's a certain amount of variation from one gas station to the next. So in other words, there is some average for the entire population, which we don't know, but we are pretty sure that it's somewhere in this range. Okay, it could be anywhere from $2.99 to $3.39 with 95% confidence. And by the way, that implies that there's still a 5% chance that it's outside this range. Okay, but that's a chance we're willing to take. We can't ever have complete perfection. We can't know that population mean without actually gathering up the entire population data. So for anything short of that, this is the best alternative. So what we did then was we went through and we saw how we actually calculate these intervals. The basic logic is that for the mean, you're taking X bar and adding and subtracting what we call a margin of error. The margin of error itself depends on our knowledge of one thing, and that's the population standard deviation. So we started with a case where we do know that, and we saw that the margin of error is taken from the standard normal distribution, Z, but we also need to include the standard deviation and the sample size. We also saw that this alpha is here to tell us or represents the level of confidence that we're working with, and that uniquely determines the value of this Z-score, which is sometimes called a critical value. So we can look that up in a table. Now, the right-hand side of this expression is, of course, our margin of error. X bar is our point estimate, but this is the margin of error, which shows me how much uncertainty there is associated with X bar. So the whole thing is the margin of error, but this term on the right by itself, sigma over the square root of n, is sometimes called the standard error of X bar. Z by itself is often called a Z-score or a critical value, and the alpha itself is often referred to as the level of significance. So for example, if we have a 95% confidence level, then we have a 5% level of significance. The two of them always add up to 100%. All right, let's see. So we went through and calculated some Z-scores. For example, when a 99% confidence interval, the Z-score is 2.576, because that 1% alpha that we're not including in our confidence interval is split up between the two tails of the normal distribution. So these Z-scores represent the borderlines between the upper 0.005 or 0.5% of the distribution and the bottom 0.5% of the distribution. The other way to think about it is that the probability of being between plus or minus 2.576 is 99%. We did the same thing for, oh, and by the way, how do you find these on your calculator? You just have to be a little careful. You're using the function INV norm, And just be aware that when you're looking for the z-score, like the z alpha over 2 in the upper right-hand corner here, what you're focusing on in norm is everything below that, including that left tail. So in this case, if you notice, the area that we chose is 0.995. And that does in fact give us the z-score of 2.576. If you had typed 0.005 here, you would have gotten a z-score of negative 2.576. Okay, which would tell you, I mean, it's the same thing, only with a different sign. So those are, this is how you can go about calculating these z-scores. It's pretty straightforward. And we tend to use the same ones over and over again. I did mention that confidence intervals tend to be at the 90% level, 95, 99. There's really only 3 that we'll be using in this class. So you basically could actually memorize these z-scores because there's only the 3 of them. Okay, then for 95%, this becomes 1.96 because 2.5% is an ether tau. And then finally for 90%, that drops down to 1.645. So that's pretty straightforward. Once you have that done, then, oh yes, go ahead. Oh, that's how the standard normal distribution is defined. Okay, so when you see a z-score, it's understood that it's taken from the standard normal distribution. All of these results are based on the standard normal distribution. And so when that's the case, the mean is 0 and the standard deviation is 1. Okay, so if it doesn't say that in the problem, that's what you should assume. And if you notice with the calculator, when you don't tell it otherwise, it assumes that you mean 0 and 1 because that's the most common situation that you'll be using. So yes, these results are all based on the standard normal distribution, which is the one with the mean of 0 and standard deviation of 1. It doesn't have to tell you that in the problem. In the other chapters, we were using other normal distributions, but those were different situations. For confidence interval, you always use the standard normal. All right. Yes, so yes, it's just understood that that's what you're using. So anyway, so then we went through and did an example. Now in this case, the key detail is that we know the population standard deviation to be 20% sigma. The sample size is 10, and the sample mean is 8%. And by the way, if you notice, even with such a small sample, we're still using the standard normal because we know this population standard deviation. Now, in practice, what can happen is even if we don't actually calculate the population standard deviation, sometimes we're willing to live with an assumption about it. So we're essentially saying here that if the population standard deviation is known, or if we are willing to make an assumption about it, we can use the normal distribution. Otherwise, we'll end up using what came next, which is the t distribution. So we plug the numbers in. Now, of course, in each case, for each confidence level, we'll need a different z-score, but the rest is exactly the same. So like here's the first one. This was our 90% confidence interval. And because of that, the the z-score is 1.645. And the rest we just plug them in. So our margin of error is 0.104, whereas the mean or point estimate is 0.08. So that gives us this range of values within which we think the population standard deviation, the population mean is. Now, this is a very wide interval. If you notice, the margin of error is actually larger than the point estimate. That's because the standard deviation is quite a bit higher than the mean. So that means these are very risky stocks in this portfolio. Their prices can change a lot from one day to the next. So the standard deviation is quite high, and the result is a very wide confidence interval. Then when we go to 95%, the interval gets even wider because the z-score goes up. And therefore, the margin of error goes up. Okay, if you notice, when we go to the next slide, this 1.645 becomes 196. The entire right-hand side of this equation goes up, and therefore the interval has to get bigger. Right there. So 196, and all of a sudden, look, the margin of error jumped up to 0.124. So what we're essentially claiming here is that in order to be more confident about our results, we have to include more values in our interval. I think that makes common sense. In order to be more sure, we have to allow for more possibilities. And then in the last case, the 99% confidence interval, the z-score jumps all the way up to 2.576, which makes our margin of error even higher, about 0.163. So this interval is quite wide. But the advantage of it is that we are quite confident that the true mean is in here somewhere. So for whatever, we don't know what purpose this is being put to, but at least we're quite sure that it's in here somewhere. All right, now I did show you this calculator shortcut. A lot of this work can be avoided if you use this stats menu. If you go to stat tests, and with this data, now keep in mind, since we know the population standard deviation, we're automatically using the z-score in our confidence interval. And as far as the calculator is concerned, it's called a z-interval then. That means it's a confidence interval that involves the standard normal distribution. The rest of it, you're just plugging in the numbers you have. And of course, at the end, you're putting in your confidence level. And at C level means confidence level, 0.90. And there it is. It's done all the work for you. Look at that. But it's important to understand where this came from. So even if you use the calculator, it's very important and very helpful to yourself that you know what it was doing behind the scenes. This is what it was doing. Okay, so, or actually it was this case. And of course it'll get the same results, but you have to know which one to use because there's another one that you could choose too. So you have to understand which interval is appropriate under which conditions. So then it jumps up 95. This is 95, and then this is 99. So in each case, all you're changing is this C level. Okay, now when sigma is unknown, which is probably the most common case, we use, of course, the sample standard deviation to take its place, but now we're replacing the normal or standard normal distribution with the t distribution. Okay, that's a completely new distribution, which has a lot of important properties that are similar to the standard normal, but the key detail is that this t distribution is wider than the standard normal, which incorporates the assumption that there's more uncertainty here. So in other words, not knowing the population standard deviation increases the uncertainty associated with this estimate, which means the interval has to be wider. The interval will always be wider if we don't know the standard deviation than if we do. And in fact, this is why Gossett invented the t distribution in the first place, because he recognized that the normal distribution was not appropriate in these cases. So he wanted to create something that took its place. And of course, we've been using it ever since. It's too bad he couldn't have gotten royalties for this discovery, but that's not the way it works in academia, is it? So anyway, so here's the one thing we have to watch out for with the t distribution. We always have to specify the so-called degrees of freedom. With confidence intervals, that's always going to be n-1, which keeps it simple. But in other applications, it could be very different. So often when we do tests with the t distribution, the number one priority is to keep track of the proper number of degrees of freedom. Luckily, in this case, like I said, it's very simple. It's just simply sample size minus 1. Okay, so like I said, we went over this briefly. The t distribution was invented by Gossett at the Guinness Brewing Company. He published it under a different name because his employers insisted on it. They didn't want to discourage their workers from publishing research, especially the head of quality control, but they didn't want anyone to realize that he was talking about the Guinness Company because they were afraid that somebody would steal their secrets or something. And their fears were pretty justified because apparently Gossett's immediate predecessor was fired because he was engaging in industrial espionage, meaning he was selling trade secrets to other companies. I don't know what happened to that guy, but that's why they were so nervous about publications. Anyway, But the whole point of the t-distribution is to explain the properties of the sample mean, or X bar, when we have small samples. And of course, with the t-distribution, it's understood that we do not know the population standard deviation. In reality, that's going to be the case most of the time. So that's why this proved to be so important. Because if you look at empirical research, you'll see that the majority of the time we're using the t-distribution, not the normal. All right, what do we know about the t-distribution? Well, we briefly covered this already, but let's just review it a little. It's a continuous distribution, which means that there's an infinite number of possible values. It's symmetrical about the mean. The mean is 0, and it's a bell-shaped curve. So far it looks just like the standard normal, except it's more spread out, which means there's less area in the center and more area in the tails. All right, that's why it's so useful in using analyzing the properties of sample mean when we have small samples or do not know the population standard deviation. And by the way, so we're going to introduce a new Greek letter here. This Greek letter nu is often used to represent degrees of freedom. And up here, I just want to remind everyone that all of these different probability distributions are uniquely characterized by one or two values, which are often called parameters. The binomial is characterized by the number of trials and the probability of success. Poisson is uniquely characterized by the lambda, or average number of events per unit of time. The normal distribution is uniquely characterized by the mean and standard deviation. And finally, t only is characterized by one thing, and that's nu. All right. So degrees of freedom, in this case, it's different for every application, but here it's n-1. And let's jump ahead a little bit here. And so just a quick reminder, the blue curve is t with nu equals 5 degrees of freedom. Green is the normal, standard normal. And, the difference is pretty subtle. I think you'll agree, but it's important. The blue there's not quite so much area in the center, and there's more area in these tails. You see how the blue tails are bigger than the green tails. Okay, but there's less. So in other words, you're more likely to get extreme outcomes with the t than the standard normal. And now here, when the number of degrees of freedom is 30, you see how it's almost impossible to tell them apart. That's one of the other unique characteristics of the t-distribution, is that as the degrees of freedom increases, it gets closer and closer to the standard normal case. At some point, we don't have to make a distinction between them, and then we could use either one. So that is kind of interesting. Anyway, we have moments defined for all probability distributions. This is no exception. For the t-distribution, the mean is 0, just like the standard normal. This is where they differ, though. The variance equals nu over nu minus 2. Instead of, in the case of the standard normal, 1. Now, I just want to remind you that we had two examples here. Hold on, I'm looking for my marker. I just want to make a note here so you can see. All right. Here it is. Okay. All right. So in other words, remember we had 5 degrees of freedom in those two charts I just showed you. One had 5 and one had 30. So when nu equals 5, the variance is nu over nu minus 2, which is 5/3, which is 167. Wow. So you can see the standard normal variance is 1. So this variance is 2/3 larger than the standard normal case. But when nu is 30, look what happens to that variance. It's 30 now over 30 minus 2, which is 30 over 28. And 30 over 28 is equal to approximately 1.07. So that's much, much closer to the standard normal variance. So this is why the T curve is getting so close to the Z curve when we have 30 degrees of freedom. Look how much closer it is than when we had only 5 degrees of freedom. The variance is dramatically higher with 5 degrees of freedom, but it's almost the same with 30. And so as we keep increasing the number of degrees of freedom, the variance of the T distribution will get closer and closer to 1. And the curves will sooner or later be virtually identical to each other. All right. So with all that being said, and there's of course the standard deviation. Now we have tables for the T distribution, but we can also use our calculators. So here's a small subsection of our table. If we have 9 degrees of freedom and a tail area of 0.05, then 1.833 is the appropriate T-score, as it's called. So let's say, for example, I was looking at something like this. This would be Tn minus 1 alpha equals T, 9 degrees of freedom. That means alpha was 10. The tail area is 0.05. And this equals 1.833. Now, I'd like you to note here that if this had been the standard normal distribution, you might recall that this was equal to 1.645. So the T-score will always be larger than the corresponding Z-score. And that's intentional. That's the whole point of this, because this helps us represent the fact that there's more uncertainty with the T distribution than with the standard normal. All right, so whatever T-score you get, it'll always be larger than the corresponding standard normal score. Okay. Let me just check one thing here. Ah, yes. All right, but now that T-score can be found easily with the calculator, of course. You need two things. You need an area and a degrees of freedom. This is found in the same menu that we found normal CDF. It's called INVT. It's one below INV norm. And it stands for the inverse of the T distribution. And so for this case, what we could have done, instead of looking in a table, oh, and by the way, you have to watch it with this thing. Even though the right tail area is 0.05, you're actually going to put 0.95 in there, because what this function is doing is it's looking at everything below a specific point. Okay, so in other words, if the right tail is 5%, everything below that is 95%. And the INVT function is focused on the area below that point rather than above it. So make sure you put this in. Now, if you had put in 0.05, it would not be a disaster, though, if you use 0.05, the T-score would have been not wrong, but would have had the wrong sign. It would have been negative 1.833 because of the symmetry of the curve. So just be aware of that. If you put in the 0.05, it's not that it's technically wrong, it's just that you're getting the wrong sign. And also some calculators are not defined for the left tail of the T distribution either. I think Excel is like that. If you had put in 0.05, it just would have said, no, sorry, there's no such thing. So this is why this is happening. All right, so here we go. Formally, this is the confidence interval when the sigma is unknown. And of course, the margin of error is everything on the right, of which this piece is the standard error. All right, So now we're going to do an example for the first time with the t-distribution only. So we have a university with 10,000 students whose GPAs are normally distributed. A sample of 10 students is chosen. The sample mean is 3.10, and the sample standard deviation is 0.25. All right, so what do we know? By the way, in these cases, in chapter 9, the only chapter in which the population size actually makes a difference is 8, with the sampling distributions for X bar. In this chapter, this information is nice to know, but it's not relevant to our calculations. All we need is the sample mean, the sample standard deviation, and the sample size. Okay, so we're going to calculate the 3 confidence intervals, 90, 95, 99, using this information. So what I did here is I went through and calculated all the appropriate t-scores. And like I said, you can do this with a table or with your INVT function in your calculator. So we've already seen this one for 95%. We'll see what that is. But so here's the information we have. So this is the t-score we just looked up. This is our margin of error. All right, so, and then this is the sample mean, and let's see what we get. Just give me a second to catch up. And so the final result will be 3.10 plus or minus 0.1449. So the GPA for the entire university is thought to be between 2.955 and 3.2449. Now, you notice how this time the interval is quite narrow. That's because the standard deviation was much smaller than the mean. So here, the range of possibilities is quite small, although it will get bigger as we increase the confidence level. All right, so let's try 95%. So you know already that the only thing that's going to change is the t-score. It will get bigger as we move further out into the right tail of the distribution. All right, so let's see what that turns out to be. .262 is the new t-score, which again, you can find that out with your calculator, the INVT function, or else a table. The rest of the numbers are exactly the same, but with a larger t-score, of course, the margin of error will be bigger. All right, so let's see what that turns into. Just a little bit wider. Remember, the last time the margin of error was about 0.14 something, 1449. So the margin of error did go up as we predicted. The interval is still not that wide, but it's wider than it was with 90% confidence. Okay. Now let's try 99%. Now, wow, this is getting pretty big. The t-score is all the way up to 3.25. So as you get out to into that upper and lower tail area of the t-distribution, the values get quite large. Remember, the equivalent for the standard normal was only 2.576. So the spread is getting much bigger. So we plug in the new numbers. And let's see what we're going to get. And as usual, this is the t-score. This is my margin of error. Nice. All right. So Let's go see what the final result is. Okay, so again, the margin of error got a little bit bigger. And so now the range is between about 2.84 and 3.36, let's say. That's it's a wider range, but it's still not huge compared to what we saw before in a previous example. So, but the logic is exactly the same as what we did when we knew the population standard deviation. So the only difference now is that we're using t-scores to reflect the greater uncertainty. All right, now with the calculator, remember before we use z-interval, let's go back and revisit that for a second. The function that you need now under stat tests, here it is. The only thing that will be different now is that you'll be using t-interval, and the sigma will be replaced by s. Other than that, it'll be exactly the same process. Okay, just remember now it's t-interval. Don't pick the wrong one. If you do, you're going to have trouble. So here it is. And the only thing I want to point out is that in this calculator, they use the letters SX to represent what we call S, the sample standard deviation. Just be aware of that. And you see on the bottom is our old friend C level. For confidence level, we'll start with 90. And of course, we'll get the exact same numbers because the calculator is doing what we were doing. Now, here's an interesting side note, by the way. If you do type in these numbers, you'll notice that unlike with the normal cases, when we're doing the t-distribution, did you notice that it hesitated for a few seconds? It took a little bit longer to calculate it. That's because the t-distribution takes more time to calculate than the normal. It has something to do with the way the function is calculated. But it's kind of noticeable. If you do it, you'll say, hey, wait a minute, what's going on here? Why is it taking so long? It's because the t-interval, or the t-distribution rather, is more complicated to calculate. So anyway, now with 95%, nothing changes except the C level. And as a result, we get a wider interval, just the same one that we had before when we did it with the algebra. And then finally, of course, 99%, we just change the C level, and voila. Nice. All right, now there's one last topic in this chapter. So far, all the confidence intervals we've constructed were based on the population mean. We're going to do the same thing now with the population proportion. The reason why we're doing that in this chapter is because we're going to use the standard normal distribution when we estimate the population proportion. And I think we've already had this discussion before. That's because the population proportion follows the binomial distribution, which in the limit converges to the normal distribution. So that's why we'll do it here. So the confidence interval here is slightly different, of course, but the logic is the same. You have a point estimate, where, by the way, P is the sample proportion. We don't actually know the population proportion, otherwise we would just use it. So that's P. And then here, of course, we have a z-score, which is exactly the way we did the population mean. This is now all referred to as the standard error of the sample proportion. P. And then the whole right-hand side, I guess I'll circle it in here, is the margin of error. Of course it is. So the logic is exactly the same. You have a point estimate. You have either a t or z-score. In this case, it's the z-score multiplied by a standard error, which provides you with your margin of error. All right, so let's do some examples. All right, here's one. We choose a sample of 105 fast food restaurants. Of these, 74 offer at least one vegetarian option. So we're going to use from now on the letter X to represent the number of elements that have a particular characteristic. And of course, is the sample size. So that means in our sample, the proportion who have a vegetarian option is 0.7048 or 70.48%. Now, the sample size, so if you look back here, we're basically already done because all we need is P and N. Then, of course, the z-score works the same way it did in the previous examples with the population mean. For example, with a 90% confidence interval, our z-score is 1.645, which again, we can find with a table or our INV norm function on the calculator. So we plug them all in. It's a bit messy, but not that bad. Anybody can do this. You just have to be a little careful. And if you notice in the square root, it's p times 1 minus p. And you can think of that as success and failure, because remember, this is basically a binomial, the binomial distribution extended, because every restaurant either does or does not offer the vegetarian option. Now, what does that turn into? When you do all the algebra, or calculations, I should say, let's see what that turns into. Okay, so everything in the square root turned out to be approximately 0.0445. As far as rounding is concerned, usually 4 decimals, digits after the decimal is usually sufficient, unless they're unusually small numbers. Because remember, these are estimates anyway. We don't need them to be perfect, but usually 4 places is sufficient. And when we multiply that by our z-score, the standard error is actually quite a bit smaller than the sample proportion. So the range is between 63.16% and 77.80%. So we're saying that in the general population, we would expect that the proportion, the whole population, is in this interval, with 90% confidence, that is. Which means that we're leaving room for the possibility that it's still outside that range. It's not likely, but it's possible. All right, now for 95, the only change is the z-score jumps up to 196. And that's, of course, going to make our interval a little bit wider because the margin of error will be bigger. Of course it will. Okay, so what's different this time? 0.0445 compared to, I think there's a problem here. I think there's a typo in my slides. No, there isn't. Oh, I just realized, no, this should be the same. What's wrong with me? This number should be the same as what we had the last time. Remember, the actual standard error is what this represents. It's the same for each case. This is what changes. False alarm, there's no mistake here. This is the new z-score. The margin of error is a little bit bigger, and our range is a little bit wider. So all that remains is the 99% confidence level, where the z-score goes up even more to 2.576. So let's see how that works out. I've changed that to 2.576. And finally, so our margin of error gets even bigger. And there we go. That's our final result. So you're probably wondering, is there a function in the calculator that can do this directly for us like there was for the other two cases? And the answer is yes. You just have to know which one it is. All right, so I'm about to reveal the mystery to you. So if you go to your calculator under stat tests, it's called one prop Z interval, meaning one proportion Z interval. There is no such thing as one prop T interval. We only use the standard normal with the proportions. So all that really matters is, do you have one or two proportions? No, we're not going to cover the case of two proportions. That has to wait for a more advanced class. But for our purposes, this is the one we'll use, one prop Zint, which is, I forgot to write it down, which number this is. Hold on. It's 5. One prop, no, sorry, that's the wrong one. Whoops, no. It's A, letter A, one prop Zint. Okay. If you pick the wrong one, as usual, you'll know right away because it's asking you for information you don't have. If you really do get the wrong one, it should be clear that you've picked the wrong one because it's asking you for things that you just don't know. So here, all it really wants is X, N, and the C level. Then you'll hit, of course, the calculate button on the bottom, and this is what you'll get. So remember, X is the number of restaurants with the vegetarian option, N is the sample size, and this is my confidence level. So it's really, really easy. All right, now there's just one more topic. This is an interesting concept, what we're about to do. We're going to flip all of this on its head a little bit. We're going to essentially come at this from a different direction. Unfortunately, what we're about to do doesn't have a special formula in the calculator, but that's all right, because the formula we'll be using is not that complicated. Now, if you notice, in all of these cases, we have the same setup. We have, for example, here, we have a score, Z or T score. We have a standard error, and we have a margin of error. Now, let's just say that for some reason, like with our 90% confidence interval, the margin of error is about 7%. So we're basically saying that the true proportion is about 70.5%, give or take roughly 7.32%. What if that's not good enough? What if we need to be more specific, more precise? The only way you can reduce this margin of error is to increase the sample size. If you increase the sample size, if you notice in this ratio, if you increase the denominator of any ratio, the entire ratio gets smaller. So if I really need more precise information, the one way to do that is to get a bigger sample size. Like here, for example, the sample was 105. Had it been bigger, let's say 200 or 300, then my margin of error would have been smaller and my result would have been more precise. So what we're about to do is this. Suppose that I know for a fact that I must be within 2% of the true value. How big of a sample do I need to accomplish this goal? That's what we're about to do. We're going to try to figure out the sample size that we need to keep our margin of error at a specific level or better. Because I might, like I said, I might have some reason why I must have the correct answer within 2% instead of 7. So there's two cases that we're going to consider. Number one, the population mean. So we're going to be looking at the minimum sample size needed to achieve a specific margin of error. All right, now the formula is right here. This is the population mean, by the way. This is my z-score. This is my population standard deviation. This E is the margin of error. Okay, we're just going to call it E. So you can see it's not a complicated formula. Not at all. All right, so for example, by the way, I just want to point out something interesting. We're going to use, whether we know the population standard deviation or not. If we don't, we'll just use S squared here. So in other words, this will be the standard deviation, or the variance rather, whatever we happen to know. If it's the population, we'll use sigma. If it's not, we'll use S. Okay, either way, it's just the standard deviation squared. All right, here we go. A retail chain wants to estimate the mean amount that each customer spends in its stores with a 95% level of confidence. They discover that the population standard deviation is 10, and they want the margin of error to be no more than $2. Okay, they need it to be very specific. What sample size do we need to make sure that this margin of error does not exceed $2? So you know it's this type of problem because it says the words, what sample size is needed? All right, we're not being asked to do the confidence interval. We're asked for the sample size. All right, here we go. Let's plug in the numbers. As you know, with 95% confidence, we've already seen this, or you can look it up in the tables if you need to. The z-score is 1.96, which we square. The standard deviation was given to us as 10, which we square. And remember, the margin of error, we want it to be no more than $2. So when you plug in all those numbers, this means that the sample size is 192.08. Now, here's an important detail. You can't have a sample size of 192.08, can you? It has to be an integer. But you'll be surprised to hear that we're not going to round it down to 192 like you normally would. With these problems, you always round up to the next integer. So the proper answer here is actually 193. All right, so even if it's 192.000001, you're going to round it up to 193. So that takes some getting used to. Just remember, in this application, you always round up. All right. Other than that, we're done with this example. Now let's do the same thing for the population proportion. Here's the formula. And you can see it's a little different because we're dealing with proportions now. But the same logic really holds. I mean, it's the z-score again. We've got the error, margin of error. But here you've got P1 minus P instead of sigma squared. Okay, now let's try an example. The same retail chain. Oh, let me leave it there for a second so you can copy it. So yes, once you're told what the confidence level is and the desired margin of error, maximum margin of error, that is, this information we need because it's the population proportion that we're studying. All right, here we go. Here's our first example. The same retail chain wants to estimate the proportion of customers that use their own credit card for purchases at the 90% level of confidence. They determine that the sample proportion is 0.25, but they want the margin of error to be no more than 2% or 0.02. In that case, what sample size must they take in order to achieve that objective? Okay, so again, you notice the magic words are what sample size. All right, so this is the formula. Now remember, it's 95%. Oh no, there is a mistake. Oh. All right, I'm sorry. That was supposed to be 95. All right, just let me make a note of that. Okay, that was supposed to be 95. Sorry about that. So, and then the 0.25 is the sample proportion, which means, of course, 1 minus that is 0.75. 2% is the desired margin of error. And here, of course, you see that it's 450.19, which means we round it up, the magic word there being up, to 451. Because we always, with these cases, because remember, what we're trying to do is hit a limit of 2% in our margin of error. If we round it up a tiny bit, that will reduce the margin of error, which is what we want. All right. Now, the next chapter ties in actually very closely with this one. You'll see when we're done that what we're doing in these two chapters is essentially two equivalent ways of getting at the same results. But this next chapter has a lot of terminology in the early going that we have to get used to. So it can't be helped. But once we get through it, you'll see that it's not that complicated. And the calculators can help us out. So don't be too horrified when you see all the new terminology with this chapter 10, which is called hypothesis testing. Now, if you took any science classes in high school, you probably learned about hypothesis testing. For example, what if your hypothesis is that if I combine these two chemicals, they'll turn into something explosive or something like that. With chemistry and physics and all the other lab sciences, you can test hypotheses and actually carry out experiments. That's not going to happen in most disciplines, like economics, for example. You can't actually do experiments. All you can do is draw conclusions from the data that you have. Like if you've gathered up, like the store with the retail customers, if they want to know how much people are putting on their credit cards or something like that, they've got data, but they can't actually carry out experiments. Not really. In marketing, they might be able to do something like that. Like offer people two different brands and see which one they like the best, things like that. But with economics and finance, typically you're just stuck with the data that you have. So a hypothesis test is designed to get information about a value like the population mean, for example, but in a very, very rigorous way. So there are 6 parts to this. Now, you can write these down, but what's more important is we understand them as we go along. So that you can see this is going to take a while to get through these definitions. The first 2 are hypotheses, 2 different types of hypotheses. There's always 2 hypotheses with any test that we might carry out, which we'll explain as we go along. The level of significance you encountered in chapter 9, this is alpha. All right, so that's our alpha. The test statistic we'll see is a value that we construct to determine if our hypothesis is true or false. The critical values are either t-scores or z-scores that let us make a decision in part 6. Okay, so you can think of them as benchmarks that we can use for comparison when we make a decision. All right, so let's go through these one at a time and really understand what they mean, because this is the heart and soul of what we're doing. Okay, the calculations can come later. All right, null hypothesis. The null hypothesis is a statement that we assume is true unless there is strong contrary evidence to suggest otherwise. In this chapter, the hypotheses that we'll be testing will involve the population mean or the population proportion. But it can be applied to any of the others, like the variance or the standard deviation. The only reason why we can't do that here is because they require the use of a probability distribution that we haven't been introduced to yet. So again, if you do take another stats course, you'll run into a lot of these cases. And if not, well, at least you know what a hypothesis test is, and that's very, very important. All right. Now, here's an example which has nothing to do with finance or economics, and you see this on TV all the time. A jury trial. Now, if you've ever seen a show like Law and Order or anything along those lines, you know that the way our justice system works is that when you walk in the door and you're on trial, you have the presumption of innocence. In other words, the jury is supposed to assume that you are innocent unless strong evidence is presented that suggests that you are guilty. Okay, so in other words, you are not supposed to convict somebody unless the evidence is really, really strong. In fact, the standard is called beyond a reasonable doubt. Okay, reasonable doubt. So in this case, the setup, it's a very conservative process. They're going to assume that you're innocent. It's up to the prosecutors to prove that you're guilty. Otherwise, you go free. And that's how it's always worked. If it was the other way around, there'd be a lot of people in jail, let me tell you. But here, instead, you have the presumption of innocence, but if they have evidence against you, you could be convicted. So let's say somebody has an actual picture of you robbing that bank. Well, then I guess you're going to reject this hypothesis and find this person guilty. Now, this is written in a very specific way. We're talking about the hypothesis. Right now, we're starting our discussion with hypothesis testing about the population mean. So we write our hypothesis in this very specific way. This little zero means that this is the null hypothesis. Okay, this is the standard notation. By the way, null, you don't hear that very often in the US. In Britain, they use it more often. It actually means zero or nothing. Zero, the null. Now, this is a constant that we specified. For example, what if we want to find out if the mean amount that people spend in McDonald's is, let's say, $8. The average customer walks in the door, they spend $8. The company wants to know this. It's important information. They might want to test a hypothesis that the mean spending of our customers is $8 per person. And that is how your test would be set up. And maybe if it's lower than that, they'll have to take some steps to do something about it. All right. Now, what happens is that we assume, and by the way, in this case, let me just add one little detail here. If enough evidence is shown that the defendant, as he's called, is guilty, the null hypothesis of innocence is rejected. The word we use is reject. And the alternative hypothesis is accepted in its place. So the way it works is that if we have powerful evidence of guilt, we reject the null hypothesis that this person is innocent, and we accept the alternative that he or she is guilty. So the key words there are reject. Reject. We reject the null when we have evidence against it. Now here, like I said, the standard is beyond a reasonable doubt, which is kind of hard to quantify. Luckily in statistics though, we will see that the decision as to whether or not to reject this hypothesis comes down to a very specific number. So it's easier to say yes or no, we should reject this hypothesis. In the real world, it can be tricky. There can be gray areas with innocence, especially in guilt. It can be, let's just say, very interesting. With statistics, no. We're comparing one number to another, and we make a decision based on that. And that's all it's all numbers. All right. So the alternative hypothesis is what we'll accept in place of the null if the null is false, or if we've found evidence to reject it. So this would be the case of guilt in a jury trial. We found evidence that this person did the bank robbery, therefore they're guilty. We reject the null that they're innocent and accept the alternative that they are guilty. All right. Now, by the way, we choose the alternative. This is an important detail, which we'll get to as we go through this. The alternative hypothesis can actually be expressed in three different ways, not with a jury trial. There's only two things, innocent and guilty. We don't have different degrees of guilt, let's say. But with this hypothesis testing about a population mean, there's actually three potential alternatives that we could use. And they have three different names, which we'll get to as we go along. And they refer to the normal or t distribution. So when we write a hypothesis test or carry it out, we need to specifically mention or state what type of alternative hypothesis do we want to use? Two-tailed, right-tailed, or left-tailed? All right, so we'll get more into this in a few minutes. Actually, we're going to get to it right now. I see I'm looking ahead a little. I want you to see what this looks like with the symbols. All right, so once again, there's three possibilities. And also, I want to point out one more thing too. I don't think I mentioned it earlier. This little one here means that this is an alternative hypothesis. The 0 is for the null hypothesis. The 1 is for the alternative. So the two-tailed test simply means that if we find evidence that the mean is not equal to this value, then it's simply different or not equal to. The right-tailed test means that our population mean is greater than this number, and the left-tailed test means that the population mean is less than this number. All right, and when we do the actual test, you'll see why they're called tails. Okay, it has to do with regions under either the standard normal curve or the t-curve. All right, let's start to take a look at a quick example of all of this. And we'll work with this example as we go along and introduce all the components of hypothesis testing. The government of a small country is interested in studying the characteristics of its household incomes. They want to know if the mean household income is greater than $25,000 per year. Let's say that 10 years ago, it was 25,000 or it was less, whatever. They want to know if household incomes are growing. So they're going to test the hypothesis that, or they want to find out with a hypothesis test, if the mean household income is now greater than $25,000 per year. It's important information. In fact, there's some steps that they want to take if this turns out to be true. Now, in a case like this, the first step you always do is write out the null and alternative hypotheses. Okay, so the null would be that the mean is equal to 25,000. And the alternative is that it's greater than 25,000. Now, if you notice, we said that the government wants to know if the mean income is greater than 25,000. So the alternative hypothesis can be thought of as this is what we want. we want to prove or disprove. This actually, and by the way, in spite of the way it's written, this actually includes less than or equal to. All right, so in other words, if we do not reject the null hypothesis, it could either be because the mean is exactly 25,000 or less than 25,000. We would need hard evidence to suggest that it's greater than 25,000. Requires strong evidence to prove. Okay, so the alternative, the default, in other words, we'll continue to assume 25,000 or less, but if we have strong enough evidence to show otherwise, we'll accept the alternative that the mean is greater than 25,000. So that's the starting point. Now, if you look at the list that I showed you in the beginning of 6 elements, the third element on the list, I did mention, we've already seen this before in chapter 9, is the so-called level of significance. Now, that's designated with the letter alpha. So if you recall, the way this works is that for 95% confidence level, corresponds to a 5% or 0.05 alpha. The reason why in this chapter we focus on the alpha rather than the confidence level is because it has a very specific interpretation, which we do not have in chapter 9. And we'll define this in a minute, but it represents the probability of committing what we will call a type 1 error. Now, what is that all about? Okay, it's a very specific type of mistake that we can make with this procedure. And 5% or alpha, the level of significance, tells us how likely this is to happen. Okay, so what I've done here is I've put together a chart. And that chart tells us that there are actually 4 things that can happen when we carry out a hypothesis test. 2 of these outcomes are mistakes, and 2 of them are not. All right, let's check this out. Now, if the null hypothesis is true and you reject it anyway, you are said to have committed a type 1 error. If the null hypothesis is true and you do not reject it, you've made the correct decision. Very good. If the null hypothesis is false and you reject it, again, you've made the correct decision. But if it's false and you did not reject it, that means you've committed a type 2 error. All right, so let me give you a minute to write that down. Now, obviously, we don't want to commit a type 1 or type 2 error, but there's always going to be some chance of that happening. Like I said, with the confidence intervals, even if you have a 95% confidence interval, there's a 5% chance that your interval does not contain the proper population mean. There's always a chance of something going wrong, but we can control that to a certain degree. So the alpha is the probability of the type 1 error. The type 2 error has a different name, which we'll get to in a minute. Now, why don't we tie this back to the jury trial, just so you can get a better feel of what this actually means. In a jury trial, there's always a chance of making a mistake. What can go wrong? You can convict an innocent person, or you can acquit a guilty person. So what we're going to do is figure out which type is the type 1 error and which is the type 2 error. All right, here we go. Type 1 error would mean you convicted an innocent person because you rejected the null of their innocence when you shouldn't have. A type 2 error is the other way around. You should have convicted this person, but you did not. That's a type 2 error. You let a guilty person get away. Now, here's an interesting result. The two errors are related to each other in the sense that the less likely you are to commit a type 1 error, the more likely you are to commit a type 2 error. So having less of one means having more of the other. So think about it this way. The harder it is to convict somebody, the more likely you are to let guilty people go free. But the thinking is that convicting an innocent person is such a terrible, terrible mistake that it's better to let guilty people get away than to convict innocent people. So that's why it's so hard to convict somebody with a jury trial. We want to make sure there's very little chance of convicting the wrong person. And hopefully all this wonderful DNA evidence we see on TV all the time will help make sure that doesn't happen very often. In fact, in the last 10 or 20, 30 years, whatever, several people who were actually convicted incorrectly were discovered to be innocent through DNA evidence, and they had to be let go. And luckily, in those cases, the government gives them a bunch of money to make up for it. It's not probably enough to make up for it for real, but it just happened recently. Some poor guy has spent like 20, 30 years in jail for a crime he never committed. The government gave him, I think, $1.6 million, which I don't know about you. I don't think I would take that deal. But it can happen. All right. Now, the type 2 error, that probability is called beta. All right. So remember, type 1 error is alpha. Type 2 error is beta. We also have this other concept called power, which we will not focus on in this class. It's the probability of rejecting the null when you should reject it. In other words, making the correct decision. That's 1 minus beta. All right, so finally, I just want to mention here that the level of significance, as you saw in chapter 9, we typically choose a 90, 95, or 99% confidence level, which means that these alphas are either 1%, 5%, or 10%. Those are the ones we normally use. And of all of these, the one we use most often is the 5%. It just works well in many cases. There's no real reason for it, except that it seems to do the job. All right, and so you remember, statistics is an empirical science. We're trying to, do a good job modeling the real world. So anything that works, we're going to use it, whether it's theoretically justified or not. Okay, it just works. All right, it's like a person who cooks without measuring. They start to learn how to tell just by looking at the ingredients how much of each is needed. It's kind of the same thing here with statistics. To a certain degree, you're cooking without a recipe because, or measuring, because you're basically trying to use whatever seems to be working. All right, so and it says it right here. For many applications in economics and finance, the level of significance is almost always chosen, but not always, but often chosen to be 5%. All right, so the next section, let's go back and revisit our list. We've covered the first 3 components now. These next 2 really need to be addressed together at the same time, and they lead to a decision. So I don't want to rush through that part. And we do have 2 more classes. And because we're not having a final, we're not having a final exam, we're having just this problem sets. We don't have to spend a lot of time reviewing for the final. So we can spend the next 2 full sessions finishing this up. So what I'd like to do is stop here and tomorrow start with this test statistic, which is based either on the standard normal or the t-distribution. So some of it will be familiar to you. And we'll go through and find how to make a decision. And when all this is done, we'll see how to speed this up a bit with the calculator. And then finally, we'll apply all of this to not just the population mean, but the population proportion. And then we'll be done. Okay, so man, it's like, it seems like we just started this class yesterday, doesn't it? And here it is, we're almost done. So just be, again, like I said, what your job to do now is, hopefully you've handed in everything that's already due. All that you still will have to do is the chapter 9 and 10 problem sets, and you will be 100% done with this course, which is pretty cool. We got a lot done. So now don't forget, this 9 o'clock business applies for the whole week. So tomorrow we'll meet again at 9. And at that point, we'll pick it up with test statistics. All right. So I'll see you all tomorrow.